all of those landmarks. So that the wanting to go to A to B to find whatever it is hidden is procedural learning, and declarative learning is knowing where to find it, and it improves with the number of both of them improve with the number of one thing that is implicit in procedural learning that I was completely not aware of before is strategy. And as you can imagine, the strategy for looking for something in a circular route effectively would be different from looking for something that's in a 40-story building. So thankfully we didn't do that, but only this is an implicit form, but it is, I think, very important. And I just wanted to bring it here because I'm going to get into that also later. So as I said, we are interested in the hippocampus and the cerebellum, and in the behavior test that we conducted, what do these things do? These regions in the brain do. So the hippocampus is believed to be known to be required for spatial learning and navigation, and it is also known to be required for formation of new memories. The cerebellum is required for motor control and balance, and for improved or high level of motor skills like sketching, etc. And the cerebellum, over the past couple of decades, there has been intermittent and increasing data suggesting that the cerebellum is also involved in higher cognitive function, like planning or and language. So that's not completely established yet. It is still a very hot topic of research. But what I want to point out here is that most of these things were established based on specific region studies in which specifically the hippocampus or the cerebellum had been lesioned or inactivated. And using this slide, I just want to illustrate the fact that while region studies do demonstrate that the hippocampus is required or the cerebellum is required for a particular task, like the hippocampus is required for spatial learning, it does not mean, the corollary is not true. So it does not mean that if you take away all of my rest of the brain and you leave the hippocampus, I'll still be able to navigate efficiently, right? So in conditions like trisomy, where the entire brain is affected because it is made up of trisomy neurons and all cells are trisomy, it is not an analogous situation to a lesion study where other than the part that you have inactivated, everything else is normal. So even if you see a behavioral phenotype that is similar to what a lesion animals displays, it may result from different reasons. For example, if the hippocampus is connected to the entorhinal cortex, and the entorhinal cortex is in turn receives information from many other sensory information from many other brain regions, and they both are required for the final behavioral output. And in any kind of behavior, in trisomy, or any part of the brain can be affected, resulting in the behavior task. Is that clear? So the behavior test that I conducted was that I'm going to show you today was spontaneous alternation and Morris-Watermaze. And Morris-Watermaze in turn is composed of principal and hidden platform test and the final probe test. The Y-maze is used to measure spontaneous alternation, and it's composed of a Y-shaped maze, and which can have arms called A, B, C. And the task for the mouse is that when it is left on one of the randomly chosen arms, it's supposed to explore the Y-maze. And normal mice have a tendency of going more often as A, B, C, B, C, A, C, A, D, instead of A, B, or B, 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 because they don't like to re-enter the arms that they have just explored. So that is spontaneous alternation. And the level of activity can also be sort of judged from this, because if the mouse is running around much more than its control, then it is more hyperactive. So TS65DN mice are known to be impaired in spontaneous alternation, and I saw that both my groups of TS animals, again TS sag in blue and TS nickel in red, were impaired compared to the euploid controls that are in green, and they alternated 60% compared to the euploid as 80%. And it is also known that TS65DN are hyperactive, and both of my groups of trisomic animals, sag injected or vehicle injected, had more number of entries in rounds compared to euploid group. So here, I knew that at least I wasn't doing something bad in sag injection. They were behaving similarly similar to their other trisomic animals.
Does age affect this at all?
Age doesn't, I don't know if it affects spontaneous alternation, but it probably does. It definitely affects most behavior, and it, as far as I know, the characterization exists like it gets more impaired after age.
So what age were these?
Oh, so these were all 3 to 4 months. All injected at 5 with P0 and P0 with SAT.
Do you have to train the mice before you put them in the body?
No. But you have to handle them so that at least they don't get stressed out because they are seeing you for the first time. So you handle them extensively for 3 days before you put them in the case.
Okay. Can you examine the one mouse over again?
I didn't, but some people have. They do train it for over many days. And apparently trisomic animals after, actually I forgot what the results were, but some people have done that. So next is the Morse maze, and the first part of Morse maze is the platform. And here is where you can remember my circular room. But this is a circular tank filled with opaque water, and the opaque water has a submerged platform so that the mouse can't see it, because mice, like most animals, swim like this with their head above the water, so they can't see anything under the water. And in the visible platform, this is the platform. It is conspicuously tagged by a flag, and the mouse that is dropped is expected to associate swimming towards the flag to being rescued from water, because the mouse doesn't like water, just keep swimming in the water, right? So the association is simply to swim towards the flag, it will get on the platform, and then I'll rescue it. So it's a simpler task. All it has to do is see the flag, and we move the position of the platform around, and we drop the mouse at always the same position, and then we rescue. And they do start to do it quicker and quicker as the day of trial proceeds. This is a simpler task, so we only train the mice for 1 day, but you can do it for more. The hidden platform task is more complicated, and here the platform remains submerged. It also remains in the same position. Now the mice are supposed to also find the platform again, but this time using the extra or intra-maze cues that are present in the room or even inside the circular tank. And here, as I said before, the platform remains in the same position, but the mouse is dropped in different position over each trial. Being a more complicated trial, we do 3 days of training so that the mice can actually have a chance to learn. And for every trial, there is a maximum limit of 60 seconds, and if the mouse doesn't find the platform in 60 seconds, we bring it to the platform ourselves, and it will stay there. The final test is the probe test, which happens the next day of the hidden platform test. And at that time, we torture the mice by removing the platform, and they just swim around looking for it. And it's expected that they remember the location of the platform, where they've been finding the platform for the past 3 days, and spend most time in that quadrant of the circle. So in the visible platform and in the hidden platform, the measurement of learning is by latency, which is the time the animals take to find the platform. And in the visible platform, all 3 groups of my mice perform similarly, and this has been shown before. And all trisomic sag injected or normal trisomic mice have normal learning in visible platform. And this indicates that they have the motivation to escape the water, and it also indicates that they have normal swimming abilities. The next 2 slides show the best results of my thesis, so anybody who's asleep can wake up. And in the hidden platform, historically, trisomic animals are known to be significantly impaired, and by that I mean that they don't reduce the time they learn to find the platform quicker, unlike the green line here, which is the eukaryote control animals. But very excitingly, trisomic animals injected with SAC perform similar to eukaryote animals and were always significantly better than trisomic control animals, which are impaired. And this showed that they had improved learning in the Morse database. And to corroborate improved learning, they also had improved memory of the location of the platform, as they looked for the platform in the correct quadrant for 40% of the time, similar to what the eukaryote animals did, and significantly better than trisomic vehicle animals, who were just randomly swimming in the quadrant at 25% of the time in each quadrant. I should point out here that if you shows the overlay of the trisomic sag of the three groups, and you can see that sag injected animals are spending more time around the platform, whereas trisomic injected animals are just swimming around. So anybody who has heard of the Morris waterways, in fact Morris who made the waterways experiment, generally uses it to study the functioning of hippocampus. And in fact, lesions in hippocampus lead to impaired learning in Morris waterways, which is why we believe that the hippocampus is involved in navigation. So I already showed you that we didn't see any increase in cell proliferation at P6, but it was possible that the assay wasn't sensitive enough or something. And so I characterized the adults that had undergone behavior testing, and I looked at their dentate iris again, and I didn't see any increase in the number of cells in trisomic vehicle or an increase in the volume of dentate iris in the adults that had performed better in the Morris waterways. So at this point, we were sort of wondering at the mechanism of why there is improved learning and memory in Morris waterways without any effect that we saw in the hippocampus. Because as I said, Morris waterways is generally used for testing hippocampus. But we did have the significant change and improvement in the cerebellar morphology. And while it is not the contribution of the cerebellum in spatial learning is not something somebody would automatically think of. It has been characterized fairly well by a couple of labs in Europe. One of them, their lab is the spectroscopy lab. And what they do is they surgically remove the cerebellum, half the cerebellum of rats, and then train them in Morris waterways. Those are the HCB rats here, or HC-bed rats in the next slide. And what they find is, unlike the control animals, which after a few days of training, learn to find the platform direct using a beautiful direct trajectory, because they actually now know where it is. The HCB rats have an initial tendency of peripheral circling, and they continue to and even though they do learn to find the platform in the end, they never use the smart trajectory of finding the platform directly. And to characterize this behavior pattern, the spectroscopy lab developed a score of 1 to 10, and I adopted the same scoring pattern for scoring all the tracks in the human platform test. But before going to that, I'll not go to the experiment details of this. I just want to show from this slide is that while HCB rats that have not been trained before do have a tendency of peripheral circling and before finding the platform, HCB rats that had been pre-trained can remember the strategy that they learned, strategy to find the platform that they learned before. So peripheral circling is not a default status of once your cerebellum is gone. It is just that they can never use the most optimum strategy given changing circumstances. So I modified the scoring pattern later, and 1 to 10 was exactly what Petrosini said, with 1 being the best score and 10